Hello and welcome back. In the previous video, I talked about Newton's first and second law, and I introduced the normal force and the force due to gravity. In this video, I want to talk about free body diagrams, which is a graphical way that we represent the forces being exerted on an object, and then I want to work through a few simple examples. So the steps for drawing a free body diagram is that you first draw a picture of the object that you're studying. If you're studying multiple objects, then you draw multiple free body diagrams for each individual object. The second thing you do is that you draw arrows to represent the forces being exerted on these objects. Now there's a few rules for drawing these arrows. The first is that the length of the arrow should roughly correspond to the magnitude of the force. Okay, so a large force you would use a long arrow, a small force you'd use a shorter arrow. The second rule is that the direction that these arrows point in should correspond to the direction that the force is being applied in. Okay? So taken as a whole, these first two rules are really just saying that the arrows that you draw to represent forces in a free body diagram are just the graphical representation of the force vectors. Remember that when we talked about graphically representing vectors, we said that we graphically represent vectors with arrows, and the length of that arrow corresponds to the magnitude of the vector, and the direction of the arrow should point in the direction of the vector. So that's all this is saying, is that these arrows are graphical representations of the force vectors. The third rule is really only important when you're taking the AP exam or you're taking a test and somebody explicitly asks you to draw a free body diagram. Because technically, a free body diagram does not include components of forces, and it does not include the sums of forces. Now, one thing I should say is that when you're just solving a problem on your own, and you're drawing a free body diagram to help visualize the forces that are being exerted on an object, it's okay to include components of forces and the sums of the forces, okay? In fact, I encourage you to do whatever you have to do that helps you solve a problem, okay? So if decomposing your forces on the free body diagram helps you see what's going on, then that's what you should do. But if you're taking a test and somebody explicitly states, draw a free body diagram, then your free body diagram should not include components and it should not include the sums of the forces, okay? If you want to draw another free body diagram somewhere else to use that as a reference and include these things, that's fine. But when somebody asks you to draw a free body diagram, you cannot include those, okay? You'll lose points on the AP exam if you include those things. So I want to look at a simple example. This example asks us to draw a free body diagram for a boat that is being pushed by a motor at a constant speed. So remember that when we draw a free body diagram, actually let me open up a white screen here. When you draw a free body diagram, the first thing you do is you draw a picture of the object. So let me draw a boat. Okay, so here's my boat. And then the next thing we do is we draw arrows to represent the forces being exerted on this boat. Now, you may say, well, the boat was moving at a constant speed. That's what the slide said, so there's no forces being exerted on the object. But that's not true, right? We know that there's going to be, for example, a gravitational force pulling down on the object, okay? But what this actually tells us is that if the object is moving at a constant speed, Newton's second law says that the sum of the forces has to equals the mass times acceleration. So if I move at a constant speed, then my acceleration must be 0 meters per second squared, right? If my acceleration is constant, then the change in the velocity is 0, so my acceleration is 0. According to Newton's law, F equals ma, so if my acceleration is 0, then the sum of my forces must be 0. So if I have a force due to gravity that's pointing down, there must be another force that points up and cancels that. So we can see there's going to be some kind of buoyant force that's caused by the water pushing up on the object. Now I haven't talked about buoyant forces yet. We're not going to get to that until much later in the year, but we can already see that there must be some force pointing up on this boat. Otherwise the boat would be accelerating downwards. Now, we're told that the boat has some kind of engine that's pushing it forward. So let me draw this, some kind of engine here with a propeller, and that's pushing the boat forward. So this engine exerts a force on the boat that pushes it like this. So we have a force caused by the engine. Now, again, we're told that the boat moves at a constant velocity, okay? So if there's a force pointing to the right, if I just left the free body diagram like this, the boat would be accelerating to the right, so it wouldn't have a constant velocity. So we can see there must be a force that's pushing back on the boat that cancels the force caused by the engine. And this would be some kind of resistive force caused by the water, so, you know, friction that's caused by the water rubbing against the boat. So let's look at a little bit more complicated example. So here we're given kind of a free body diagram, not really. We're given a picture here. It shows two forces being exerted on a 5 kilogram box that's sitting on a flat frictionless surface. And we're asked to find the magnitude of the normal force being exerted by the ground on the box and the acceleration of the box. So actually, before I get started solving this problem, let me just draw a real free body diagram. So here we've got two forces. We know that this object, because this is near the surface of the Earth, so we have a force due to gravity that's pointing down. And obviously now I've got a force due to gravity that's pointing down. I've got this force F1, it's got a component that points down. But I've talked about this before. When you have a box, it's sitting on a hard surface like this. The box doesn't fall through the surface. There's a normal force that points up, and it cancels the forces that are perpendicular to the surface. So this is what's happening. I said, right, that the normal force cancels the forces that are perpendicular to the surface. Okay, right, so this is my surface here. So if I call this direction here my y direction, the way we would write this as an equation is we would say the sum of my forces in the y direction is equal to 0 newtons. So the sum of my forces in the y direction, if I call up the positive direction, the normal force points in the y direction, it's in the positive direction. The force due to gravity points in the y direction, it points in the negative direction. And there's a component of F1 that also points in the negative y direction. So I'll call that F1, y. So the sum of these has to equal 0 newtons, because I have no net force in the y direction, because, again, remember, the normal force cancels all the forces that point perpendicular to a wall, okay, or to a surface. So, solving for the normal force, I see the normal force is equal to the force due to gravity plus the y component of force 1. And the force due to gravity, we talked about this in the previous video, is equal to m times g. Now, F1y, the y component of F1, let me just draw actually down here what this looks like. So F1 looks something like this. So it's a graphical representation of this vector, and it has a component that is in the x direction. I'll call it F1, x, and then I've got a component that's in the y direction. It's F1, y. And this angle right here, this one, is 65 degrees. So looking at this triangle, we can see that the y component of F1 is opposite the angle 65 degrees. So sine of 65 degrees is the y component of F1 divided by F1. So the y component of F1 is F1 sine of 65 degrees. And if I plug these numbers into a calculator, I'll get that this is equal to 89.8 newtons. So that's the magnitude of this normal force pushing up. That's how much the force has to push up on this box to stop the box from passing through the floor. Okay? Now the second part of the problem asked us to find out what the acceleration of the box is. Okay? So we know the box is not accelerating in the up-down direction, right? In the y direction, the acceleration was 0. We know that because the normal force cancels all the forces in the y direction. So the acceleration is going to be in the x direction. And there's two forces that point in the x direction. So let me go ahead and, so we have that the sum of my forces in the x direction is equal to my mass times acceleration. And I've got two forces in the x direction. If I call this direction the positive x direction, then F2 points in the negative direction. So we've got minus F2 plus the x component of F1, because the x component of F1 is going to point in the positive x direction. And that equals mass times acceleration. Now again, I have this in the previous slide. Here's my F1, and I have these components of the vectors here. So we can see that the x component of F1, that's this side right here, this is adjacent to the angle 65 degrees, this side here. So cosine of 65 is adjacent over hypotenuse, so cosine of 65 is F1, the x component of F1 divided by F1. So this right here is F1 cosine of 65 degrees. So we have that minus F2 plus F1 cosine of 65 degrees is mass times acceleration. I was asked to solve for the acceleration, so we get A is, let me write this as F1 cosine of 65 degrees minus F2 divided by the mass. And again, if I plug all these numbers into a calculator, I see that this is going to be equal to, let's see, where's my cheat sheet? Minus 1.2 meters per second squared. This negative sign, oops, that I forgot to put there, that means that the box is accelerating in the negative direction. So the box is moving to the left. It's moving to the left because F2 was greater than the x component of F1. Okay? So now let's look at one last example, and then that'll be the end of this video. This example says we have a box that weighs 5.77 kilograms. It's placed on a frictionless ramp, and the ramp is tilted to an angle of 30 degrees. And we're asked to find the normal force that the ramp exerts on the block, and then we're asked to find the acceleration of the block down the ramp. Okay, so whenever we study something like a box on a ramp, so let me go ahead and draw a picture of this. Here's our ramp, and here's the box on the ramp. Whenever you study something like a box on the ramp, it's the usual way we do this is we call this direction, it's perpendicular to the ramp, the positive y direction, and the direction down the ramp, the x direction. The reason that we choose our x and y direction like this is because I know before I do any calculation that the normal force, right, is going to cancel the component of my gravitational force that points in the y direction. Right? So I know, let me draw a free body diagram. I've got the normal force here, and I've got the force due to gravity. Looks something like this. And I know that this normal force is going to cancel the component of my force due to gravity that points in the y direction. So this is the y component of my force due to gravity, and this is the x component of my force due to gravity. So I know that there's no acceleration in this y direction. Okay? Another good reason that anytime you have an object that's in contact with a surface, you want to choose your x and y axes to be parallel to and perpendicular to the surface, is because you know that whenever an object is in contact with the surface, there's two types of forces that arise. The normal force that's perpendicular to the surface, so that'll be along one of your axes, if you choose one of your axes to be perpendicular to the surface. And then there's a frictional force, which we haven't talked about yet, but the frictional force is always going to be parallel to the surface. So if you choose your axes to be parallel to and then perpendicular to the surface, then the normal force will point along one axis, and the frictional force will point along the other axis. Even better, the normal force is going to cancel all of the forces along one of these axes, so that the motion is going to be, like for example in this case, all along the x direction. So that means that the problem is going to be a one-dimensional problem, because the motion is going to be only in the x direction. That makes it easier to solve. Now, obviously I want to figure out what the x and y components of my force due to gravity are, right? In fact, the first step asks me to find the normal force. So the normal force comes from the forces in the y direction. Oops, let me use white here. So the normal force cancels forces that are perpendicular to the surface. So the normal force is canceling the y component of gravity. So we see that the normal force, actually let me go back a little bit further. So we have the sum of my forces in the y direction is equal to 0 newtons. And that's telling me that my normal force is equal to minus force due to gravity in the y direction, or the y component of my force due to gravity. So obviously to answer this, I need to figure out what the y component of my force due to gravity is. So I need to figure out how this triangle here is related to the ramp here. Okay, and what was the angle of my ramp? I don't remember. 30 degrees. So let me open up a blank sheet real quick. So what we have is we have a ramp. It's at 30 degrees. And then I've got this box on the ramp. And the force due to gravity points vertically down. So let me draw a really long force due to gravity vector. So this angle right here is 90 degrees, right? We can see this one here is 90 degrees. Okay. This direction right here, this is parallel to the surface of the ramp. Okay. So here we've got a triangle. It's formed by this ramp and the force due to gravity. So I can see that this angle right here is 60 degrees, right? It's 90 minus 30 degrees. Okay? That means that this angle up here is also 60 degrees. Now, if I decompose my force due to gravity like this, now we can see that this angle right here, the angle between this y component and my force due to gravity, this line right here, and this dashed line right here that is parallel to the surface of the ramp, we can see that those two things are 90 degrees apart, right? The direction that's perpendicular to the ramp and parallel to the ramp, they're 90 degrees apart. So if this angle right here is 60 degrees, then this angle right here, let me do that in black, that angle right there is 30 degrees. Okay, so the way we did this is we said the ramp was at 30 degrees. If I draw my force really long, we can see that this is going to form a right triangle in here. So this is 30 degrees. This must be 90 minus 30 degrees. This angle up here is also 90 minus 30 degrees. And this direction, which is parallel to the ramp, and the force due to gravity that's perpendicular to the ramp, those two things are at 90 degrees. So this angle right here had to be 90 minus that 60 degrees, so we get back to the same angle as the ramp, 30 degrees. So let me go back to the problem, and let me just draw this vector right here, kind of blown up. So what we have here is we have the force due to gravity, and we have a component that's in the y direction, and a component that's in the x direction. And this angle up here, that is 30 degrees. And this is my y component. And this is my x component. So the normal force is just equal in magnitude in opposite direction as the y component of my gravitational force. Well, we can see, looking at this triangle, the y component of my gravitational force is adjacent to the 30 degree angle. Here's my 30 degree angle. This is adjacent to it. So that means that cosine of 30 degrees is equal to adjacent over hypotenuse. That's the y component of the force due to gravity divided by the force due to gravity. So we can see the y component of the force due to gravity is the force due to gravity times cosine of 30 degrees. Finally, the force due to gravity we know is m g. So we have mg cosine of 30 degrees. And if we plug all this into a calculator, we get that this is equal to 48.8 newtons. Okay? So that's the normal force that the ramp exerts on the box. Okay? Now, one thing I want to point out about this equation right here, I've mentioned this before, but it's really worth mentioning again, right? This ramp right here, if we consider limiting cases, there are two limiting cases here, right? If the ramp was flat, so if we have something like this, we've got a ramp that's flat and we've got a box on it. Well, in this case, the angle of my ramp is 0 degrees. And I know, in this case, the normal force is equal to the force due to gravity, which is mg. And if the ramp were at 90 degrees, okay, then I have a box that's in free fall, then the wall is not exerting a force on the box anymore. The box is just falling straight down and the wall is not pushing against the box. So in this case, the normal force is 0 newtons. So just from this alone, you can see that, you know, the probable formula is going to be mg cosine of theta. Because cosine of 0 degrees is 1, so we've got mg times 1 when theta is 0, and cosine of 90 degrees is 0. So at 90 degrees, this would give me 0. So actually, we just went through some geometry relating all these similar triangles to figure out what the x and y components of the force due to gravity were, but you don't have to do that every time you solve this problem. You can really just think in terms of limiting cases and say, well, I know it's a sine or a cosine, which one makes sense? So that's how we get the normal force. The second part of the problem asks us to find the acceleration down the ramp. Well, looking at this, we can see the normal force is perpendicular to the ramp, so it's not going to help cause the box to accelerate down the ramp. So the only force in this x direction is the x component of the force due to gravity. Looking at this triangle over here, we can see the x component of the force due to gravity is opposite the angle 30 degrees. Okay, so we can see that the force in the x direction is just the x component of my gravitational force, and that's going to be the gravitational force times sine of theta. Sine because it's opposite the angle 30 degrees. So we have ma is equal to mg sine theta. The m's cancel, and my acceleration is g sine of theta. And if I plug that into a calculator, we've got 9.8 here, and we've got sine of 30 degrees here. You see that this is equal to 4.91 meters per second squared. So that's the acceleration of the block down the ramp. Okay? So at that point, I think I'm going to end this video, and in the next video, I'm going to talk about frictional forces.